Okay, so now we're going to look at, in this video, what we do with lattice enthalpies and applying them to Born-Haber cycles, so Hess's law as applied to ionic lattices. And this is primarily how questions will turn up on your exams when we look at these. So what we need to be able to do is know what each of our delta H values in that thermodynamic data table is actually telling us about. Okay, so and understand the formation of a lattice. So in order for things to react and form ionic lattices, so metals and non-metals, there's a series of processes that need to occur. So we need to have atomization of the solid metal. So this is getting from the metallic lattice into single atoms. Okay, so we get this symbol here, delta H atomization, and this relates to the metal. Okay, so this is where we're going to get our cations from. Ionization of the gaseous metal. Okay, so delta H of ionization, this is our ionization energy. Okay, then, so now we have our cations. At this stage, we have our cation. Okay, but we don't have our anions. Now, our anions are generally going to come from halides are a common one, or compounds that are going to need to break molecules in order to form ions. So then what we have here is dissociation or atomization of the molecular non-metal into its atoms. So this one gets delta HD. So this is basically breaking the bonds, say, between a chlorine molecule, okay, to give us two chlorine atoms. Then reaction between the gaseous ions to form the solid ionic lattice. Sorry, I skipped a step. Step 4 is the addition of electrons. So this is our electron affinity value, okay, that we talked about in the previous video. So this is the energy that we get back, remembering this was exothermic, when the unstable single chlorine atom, say, picks up an electron and becomes the anion. So this is forming our anion. Okay, so this is our non-metal here that is going to form single atoms, then draw our electrons to it, and we will now have our anion formed. Okay, then we're going to have these gaseous ions come together to form the solid ionic lattice. So this is the enthalpy of lattice formation that we have here. Okay, and remembering that going from the gas to the lattice is highly exothermic. So the last step, the enthalpy of formation of the lattice, so the lattice formation here, has the same magnitude but opposite sign of the lattice enthalpy. Because remember, enthalpy of lattice formation was exothermic, and IB defines lattice enthalpy as being the endothermic process. So this here and the overall lattice enthalpy, delta HL, will have the same value but opposite sign. Okay, because one refers to the exothermic process and the other refers to the endothermic process. As we mentioned previously, as a general rule, the more negative the standard enthalpy change of formation of the ionic compound, so the enthalpy of formation is delta H LF here, the more stable the compound will be. Remembering, so the more negative this value translates into the more positive this value. And we said that the higher the lattice enthalpy, the stronger the actual lattice. Okay, so with these, it's always going to go in the same sort of steps. We need to remember that atomization and ionization are both going to be endothermic processes. So because in order to get single atoms, we're going to have to pull them out of the lattice, and then to form our ions, our positive ions, that is an endothermic process. Then for our and then 3 also is going to be an endothermic process. So in each one of these, 1, 2, and 3, we need to be putting energy in from the environment. They need energy to occur. But then when we have these two, 4 and 5, these are actually going to be exothermic processes. So depending on the overall magnitude of these, when we add these together, we're going to determine our final lattice energy. Okay. So we need to be considering which ones are endo and which ones are exo, and know what we're talking about for each one as we go. This formation of the solid lattice needs to be sufficiently exothermic to make up for those endothermic processes, okay? Because if it wasn't sufficient for that, we wouldn't get lattices that form naturally, okay? So let's have a look at what this looks like. Okay, so what we see here is the steps broken down. Okay, so sodium is being atomized to form 1 mole of gaseous ions. We get this from table section 8 of our data book. So the delta H atomization of sodium is going to be positive 107 kilojoules per mole. Then in order to form to break the bonds of 1 mole of chlorine atoms, we will take half a mole of chlorine and get 1 mole of chlorine atoms. Okay, so half a mole of chlorine will yield 1 mole of chlorine atoms. Okay, the bond enthalpy for the chlorine bond we're going to get from our bond enthalpy tables. That bond enthalpy is endothermic positive 242, but because we only want half a mole, we're going to halve it. Okay, because when we break this bond, we're going to get 2. We want 1 mole of total atoms, so we halve the bond enthalpy. Okay, so when we remove an electron from the outer shell, we have the ionization of sodium. So we're going to get that from table 8, section 8, for the ionization energy of sodium, positive 496. Then we have the electron affinity of chlorine. Okay, now we are talking electron affinity of a full mole, so this just comes off the table. Then what we want to work out is the enthalpy of lattice formation of the sodium chloride. So we can actually do this as a cycle. Down the bottom here, we place sodium chloride solid. That's what we want to get to. Up the top, and our highest energy, if we think of this as enthalpy, our highest energy state is going to be our sodium ions and our chlorine atoms. So starting with sodium solid and half chlorine gas, we add energy in to get to our atomization, okay, and break our bond enthalpy to get to 1 mole of sodium, 1 mole of chlorine. Then we ionize the sodium, okay, which will get us to our highest energy level. Single atoms of chlorine, ions of sodium. That electron is then, electron affinity is an exothermic process, so we come down to now the free ions, sodium plus and chloride minus. So the difference between this stage here and this stage here is going to be the lattice enthalpy for sodium chloride. Okay, so we can work that out mathematically. So because we can't measure them directly, we basically use Born-Haber cycles, which are applications of Hess's law, to relate these to each other. So to create the cycle, we need the literature values for all of the steps except one, okay? And we can get these from our data booklet. And then we essentially just add them together. So if we're looking for delta HF of sodium chloride, okay, this one here, which we can get from our data booklet, this bit here, okay, this bit here is essentially going to be the energy for atomization plus the energy for ionization plus the half bond enthalpy plus the electron affinity, and then minus this one here. Okay, when we do that, essentially we end up with the overall equation. So all of these are plus, we're going to add them all together. We then are going to add our here and this one here. okay, which is going to get me all the way up to here, and then we're going to subtract this, and what we will end up with is this bit here. So if we want to find this, we add them all together. So we're going to get each of the values from the data booklet, substitute them in, and we will find that the lattice enthalpy is 786 kilojoules per mole, and it is going to be a positive value because and that's this value here, this delta H of the lattice enthalpy, this one here, okay, is going to be a positive value because it is defined by IB as being the endothermic process. So essentially what we are looking at is the delta H for the lattice, okay, okay, is equal to delta H of atomization plus the electron affinity, okay, plus the delta H of the ionization energy. Sorry, E being this is your bond enthalpy. Okay, so then our ionization energy minus, ionization energy, then we have delta H of our electron affinity, okay, forming the negative ions, minus delta H, minus the delta H of formation, okay, which is this one here, which we get from our data booklet as well. Okay, so we can find this here by adding up all these values that we get from the data booklet and subtracting this one here. Okay, so we add all these together. We're going to add that one in, which is going to be negative, and we're going to subtract that. Okay, so we will end up with that value overall there. So essentially what's left for us to do is to actually do some practices. So as normal, let's have a look at these and look at some examples. So find the overall enthalpy for the formation of solid sodium chloride according to the equation. So this is basically the one of what we did here. It wants us to find the overall enthalpy of formation. So remember, this is going to be the opposite. Our lattice enthalpy would be the opposite. Okay, so let's have a look. We have atomization, ionization, dissociation of the chlorine molecules, breaking of that bond using bond enthalpies, remembering that it's going to be a half, ionization due to electron affinity, the reaction between the ions. So we can write this out completely this way, and what we will find is that it should be the delta H of formation, because this is the one that we didn't have, is minus 412 kilojoules per mole, because this was our lattice formation here. Okay. Because the question, you will note that in this one, the question is actually asking for the formation of solid sodium chloride from sodium and chlorine gas. This is not enthalpy of formation as the IB states. Okay, we're going from the gaseous to the solid, so it's actually going to be an exothermic value. Okay, so you need to read these questions and figure out which one it's actually asking you to do. Okay, so this is another way of drawing it. All of these are essentially cycles. What we're saying here, we take our solid, we atomize it, we take a half of our chlorine, we form the ions, and then this value here is our lattice formation, and this is our formation at standard conditions. Remembering that delta H of formation is the formation of a compound from its elemental components, okay, going from its elements at standard state straight this way. So this delta H of formation is by definition at standard state, so these must be in solid and a gas, which is why it differs to the lattice formation value, because that's going from the gaseous ions. Okay, if you're wondering what the difference between these two is. Okay, so then we follow it through in exactly the same way. So there is a number of questions here that I want you to work through. The questions are provided on this slide, and then come back to have a look at the solutions. The values here that you're going to need have actually been provided in this table along with the formula for you to apply. So substitute them in and see how you go. Remember to pause and then come back and have a look at the solutions. Okay, let's see how you went with the rubidium example. So this is the example here. So drawing the cycle, we start with rubidium solid, half chlorine gas, and we have the ionization of rubidium, which was plus 81 kilojoules per mole, which we see here, the atomization. That's the atomization to take it from the metallic lattice, okay? Then we have the dissociation of the chlorine bond. Then we have ionization to form the positive ion and electron affinity for the chlorine gas. So we now know that the lattice of formation is going to be negative of the lattice enthalpy. And then this delta H of formation at standard conditions we get from the data book as well. Substitute all those into the formula and you should have gotten negative 692 kilojoules per mole. Okay, but remembering that it has asked us for the enthalpy of lattice formation, so we need to change that to the endothermic process for IB. So the final answer is that the lattice enthalpy of rubidium is going to be positive 692 kilojoules per mole. Okay, so let's have another question, have another go, come back and see what the solution is. Okay, so this one's getting us to look at magnesium oxide, which is a prac we've actually done. We're going to write the equation to represent the second electron affinity of oxygen. Okay, remember, because oxygen's going to actually have to gain 2 electrons. So it will have 2 electron values. Okay, you're going to comment on the relative values of the first and the second, which are given in the data booklet. And then have a look at these to construct the Born-Haber cycle. The additional information that you required was down here, and then we're going to work out the lattice energy. So let's have a look at our solution. So the equation for the ionization of magnesium, we're going to have magnesium oxide solid, and we're going to go to magnesium 2 plus O2 gas. For the second ionization energy of oxygen, we're going to start with O minus because it's the second ionization energy's, electron affinity. So we've already gained 1 electron. So we're going to gain another electron and go to O2 minus. Remembering that these electron affinities are in staged processes, it doesn't happen all at once. Okay, so the first electron affinity is the attraction of 1 into the outer shell. Then that's going to be exothermic. The second electron affinity, okay, is the oxide accepting an additional electron. Okay, so they will repulse each other, but so it's going to be a slightly endothermic process. Because we're trying to get that in over a little bit more repulsion. So when we look at drawing our Born-Haber cycle, okay, we need to look at the enthalpy change for the atomization for oxygen. So remembering that oxygen has a double bond, we're going to need half the bond energy for O2. So we're starting here. We're going to have the atomization of the magnesium from the data booklet, plus 148. Atomization of oxygen, we're halving the double bond of our oxygen molecule from the bond enthalpy tables. Then we're going to here look at the now the ionization of the magnesium. So that's going to be 738 plus 1451. Remember, we have both stages for those, the 2 ionizations, and then we have the formation of the electron affinities as well. Okay, when we substitute all these values in, remembering negative 602 we're going to get for our enthalpy of formation of the lattice, you should have gotten a positive 3,799. And if we look at this, this indicates that the magnesium oxide lattice is actually stronger than the sodium chloride lattice because it requires a lot more energy to disrupt. Okay, so what we're going to do here is I want you to actually pause, do the questions from your textbook, and have a go at that Born-Haber worksheet that you've been given. Okay, go through and do those questions. Once you've done those questions, hopefully it will start to make a bit more sense, and we can come back and talk about lattice stabilities and then move on to solutions. So good luck with the questions, and we'll see how you go.